All right, so this is actually our review session where we are completely done with chapter two. So now it's just a question of getting a little bit more practice. So I posted this document, chapter two review problems, and I just randomly picked some problems from each different type of rule. I mean, this can't possibly cover everything, but it's a pretty good representation of the types of problems you may run into in the assignments. And so we'll start at the beginning and I'll just go through them all with you. And hopefully, this will give you a little more confidence in doing these types of problems. Of course, first we have to get used to the rules, and then we also have to develop the ability to recognize when each rule is appropriate. So that's part of it. And of course, towards the end, we'll be looking at some of the more complicated techniques like the chain rule and implicit differentiation. Anyway, why don't we start at the beginning? So here we have, um, it doesn't explicitly tell us what rules to use. Okay, so unless it specifically says, well, actually, I'm sorry, this one does tell us what to do. It's the next batch that doesn't. I wasn't looking at it carefully enough. Here we're being asked to use the definition of a derivative. All right, now what does that mean? When you see that wording, what they're actually saying is this: you must use this definition. Okay, so this is what is meant by the definition of the derivative. So you're using a limit to find the derivative instead of the rules. Now, since we know the rules, if you want, at the end, we can double check our answers with the rules. But first, let's make sure we can do it with the definition. So the tricky part here really is this f of x plus delta x. What is that all about? Well, here's what we're going to see. With f of x plus delta x, what we're doing is we're simply replacing each x in our equation with x plus delta x. Right? And so now we have to expand x plus delta x. So let's just say that we do this with FOIL. Okay, so how would this work out? All right, here's f, x squared. Here's O, x delta x. Here's I, again, x plus delta x. And then last would be these two, delta x squared. So when you consolidate these terms, you'll see that you, oh, what did I do? So this is x delta x, sorry. All right, so we've got x squared plus 2x delta x plus delta x squared. So the term in parentheses, x plus delta x squared is equal to this. So that means that f of x plus delta x is 4 times this entire expression. Right? Don't forget about the 4. All right. So you do need that. So ultimately, this is equal to 4x squared plus 8x delta x plus 4 delta x squared. All right, fine. Now, the formula asks for this, then we subtract f of x and divide by x, and then whatever that is, we take the limit as delta x goes to 0. So that means that f of, let's move it down here, or I should say the limit of this expression is therefore equal to, all right, so we just copy this part. Now, here's where we have to be careful. We're subtracting f of x. F of x is 4x squared. All right, so that makes it less risky. But if you have a fairly long polynomial, you've got to remember that you're subtracting the whole thing, which means you have to apply the negative to each term. Here, we don't have to worry so much about it because there's only a single term. Now, right about here, what's going to typically happen is there's often cancellation involved where we can drop out some of these terms. And here you can see that that's exactly what happened. So we're left with 8x delta x plus 4 delta x squared all over delta x. Now here, we can simply divide the delta x out of each term because each of the terms in the numerator has that common factor of delta x. So this reduces to 8x plus 4 delta x. Now, as you know from the previous chapter, when you take a limit like this, all you're really doing is substituting 0 here for delta x. So you ultimately end up with 8x. And you can double check that. Let's come back here. Now, let's use the power rule to confirm this. Okay. Now, when you first learned about this definition, you didn't know about the power rule and you were unable to confirm your results, but now you do know. So you might as well take advantage of that. So remember how this works? This is our old friend, the power rule, which you see, we get a lot of use out of this, don't we? Okay. It shows up quite often because often we're dealing with polynomials. And so here, the 4 is our k, 2 is our n. So we're going to have kx, oh, sorry, nk x to the n minus 1 will therefore be 2, 4, x 2 minus 1. And what do you know? It's the same. That means we must have done it correctly. Now, nobody is going to require you to do this double check, right? This is just for you. Although I think it's a pretty good idea. All right, now we're going to do the same thing with number 2. Number 2 is just a little bit more complicated, but not too much more. So once again, this one is asking us, these first two are being calculated or derived with the definition of a derivative. Okay, after that, we'll just use the rules. All right, so here we go. So once again, we might as well just go ahead and figure out what this is equal to. So we'll have 5 times delta x, x plus delta x. So remember, we're taking all these x's and replacing them with x plus delta x. All right. So it's going to take a little while, but we'll get this. Now, the x plus delta x squared we just got through seeing is, well, we'll hold on. Let's do this first. 5x plus 5 delta x. Now, we have to subtract the square of x plus delta x, which we know from here is this piece, x squared plus 2x delta x plus delta x squared. Since we just got through doing it, we don't have to do it again. But remember, this was obtained through FOIL, if you forget. But here's where we have to watch it. All of this, the entire expression is being subtracted. That's why I wrote it in parentheses to remind us. And now this negative is being applied to each of these terms. As is so often the case. Um, Well, there's nothing to cancel out here. No, there isn't, huh? All right, well, it doesn't always work out so well. But once we subtract f of x from there, then there should be some cancellation. All right, good. All right, so now our limit of f of x plus delta x minus f of x over delta x will equal. All right, so here we gotta watch it. We're probably gonna run out of room if we're not careful. So I have to be super careful with these negatives. All right, so we've got now the original function was 5x minus x squared. That gets subtracted over here. So we have to apply the negative sign here. And let's do that first. Okay, now we can reasonably expect there to be some cancellation. And so let's find, here we go. These two cancel out. Here's two more. I think that might be it. So we're left with 5 delta x minus 2x delta x minus delta x squared divided by delta x. And once again, each of these terms has a common factor of delta x. We can divide it out. And so all of this reduces to 5 minus 2x minus delta x. And now we can replace that delta x with 0. And so we end up with 5 minus 2x. Now we can confirm this by applying the power rule to this expression. So for the first term, 5x, remember the way this works with the power rule. Whenever you have a constant times x, the first derivative will be just k. The second term is minus x squared. So when f of x equals x squared, k is 1, n is 2, and f prime of x is n k x to the n minus 1, which means 2, 1, x, 2 minus 1, 2x. So that means clearly we must have done this correctly. All right, so we're rolling now. All right, let's see what's next. So here, it's not telling us which rule to use. We have to figure that out. That's our job. So this first one looks pretty straightforward. It's a simple polynomial, which means we'll be applying the power rule to all three terms. So again, let's quickly repeat what that looks like. So that means for this one, we're going to have 4 times 8 times x to the 4 minus 1 plus for this one, I'll have 2 times 9 times x to the 2 minus 1. This term just goes to 0. We don't have to worry about it. So we end up with 32x cubed plus 18x. Oh, well, that was pretty straightforward. Now, number 4 looks like it could be a problem. We have a 2 over x. Can we apply the power rule to that second term? The answer is yes, as long as we recognize that what we have here is the same thing as x to the fourth plus 2x to the minus 1. Okay, well, now the power rule applies to both terms. The first one will be 4 times 1 times x to the 4 minus 1. Second one is minus 1 times 2, x to the minus 1 minus 1. So you have to watch it with these negative exponents. Remember, you're subtracting with the power rule. You've got 4x cubed minus 2x to the minus 2 power. Or, if you prefer, you could rewrite that as 4x cubed minus 2 over x squared. That doesn't really matter, but you can see by writing it as 2x to the minus 1, I think it makes it clearer that you should be using the power rule here. Well, all right then. Now, oh, here we go. A tricky one. Well, not really. This one clearly calls for the product rule. Okay. So what this means is that here's our g of x. Remember the way this works. We're assuming that f of x is a product of two other functions. And the product rule tells us that we have this result. So here we know that g of x is x plus 2, the first term. And its derivative, based on the power rule, is simply 1. Okay, because remember, the derivative of just x by itself is 1. The derivative of constant is 0. Now here, 2x squared minus 3. So again, that the constant will have a derivative of 0. The power rule tells us then that h prime of x is just 4x. And now we just do some substitution. So as long as we're careful, we should be fine. Now that's, of course, always true. There's never going to come a time when you should be careless. All right, so it's g of x, x plus 2, h prime of x, 4x, plus h of x, which is 2x squared minus 3, times g prime of x, which is 1. So we can, you can leave it like this, I suppose, but in a case like this, it's pretty straightforward. We may as well write it out. We have 4x squared plus 8x plus 2x squared minus 3. So we end up with two like terms here, the 2x squares. The reason why this is important is because, especially with the system that we have, if you are typing in your answer, it's possible that you'll get marked wrong if you don't put it in this form. So it's good to know how to rewrite it as a basic standard polynomial. Now here we have a quotient rule. Okay. So how does that work? G of x is the numerator. Its derivative, based on the power rule, will be 12x squared minus 2. The denominator is the h. And based on the power rule, its derivative is 2x. So let's write out the quotient rule. Assuming f of x is g of x over h of x, we have okay. Actually, let me neaten that up a bit. Now we just do some substitutions. So we have x squared times 12x squared minus 2 minus 4x cubed minus 2x plus 1. And h prime of x is 2x. All divided by x squared squared. So again, if you wanted to, you could multiply these terms out and try to combine them. It's not absolutely necessary, but you know what? We'll give this a shot. You never know when you might get some simplification. Now here we've got to really watch it because we're subtracting a product. So what we're going to do is do the subtraction separately from the multiplication by 2x, just to be on the safe side. All right, we have two like terms here. We have 4x to the fourth. We have two squared terms. You know, all the terms have an x at least in common, so I can reduce this to 4x cubed is 2x minus 2 for x cubed. That's as simple as it's going to get. Now, oh, look at this. We have some trig functions. Now, in the slides, even though I didn't put them all right next to each other, all the trig derivatives are listed in 2b. I looked through the book. I wasn't able to find a chart. I probably just went right past it, but um, that actually just simply lists all the trig derivatives. But they're here. No, I guess they weren't 2a. Hold on. Let's just go find them. Here we go. All right. So here's what ended up happening. You've got first the two basic ones, the sine and the cosine. So the derivative of the sine of x is the cosine of x. The derivative of the cosine of x is negative sine of x. Then we jump ahead a little and the tangent is here, secant squared. And then the last three are down here on a separate page. Now, this one requires us to use secant x. So we're going to write this over here so we don't forget. The derivative of the secant is the secant times the tangent. So that means here I'm applying the power rule. Here too, technically. And then here I've got this. So when you put all that together, I have 2x. Now don't forget this minus sign here. And of course, the derivative of 1 just goes to 0. And that's your final result. And so sometimes these can be more straightforward than some of the other questions. It may not look like it at first glance, but trig functions don't have to be painfully difficult because we do have our charts that can help us. Now, here's one. Now, this one will require us to do a product rule with one trig function. So here, the first term, g of x is x squared, g prime of x is 2x, h of x is cotangent x, and we can look up cotangent, the derivative is negative cosecant squared. Okay, now remember the product rule, assuming f of x is g of x times h of x, then f prime of x is g of x h prime of x plus h of x g prime of x. Great. Now we just make some substitutions. Oh, sorry, that's not squared. Okay, so now we'll just neaten it up a little bit. Usually when we have a product of like a polynomial and a trig function, we usually write the trig function last. It's not absolutely necessary, but that's the convention. So this is your final result. Okay. Now this one clearly is going to ask us to use the quotient rule, but including a trig function. So we have g of x, secant x, and based on our chart, that one, oh, that's right, we already saw that one. Denominator is pretty straightforward. I mean, h of x is x, h prime of x is just one. Okay, great. So therefore, let's use the quotient rule. So assuming that this is the ratio of two functions, the derivative, according to the quotient rule, is okay. So now we just do some substitutions. Now, sometimes with trig functions, by the way, you might find that you have an identity or of some kind that can be simplified, but I don't think that's going to happen here. Well, x secant x tan x minus secant x times 1 over x squared. You can simplify it a little bit just by rewriting it as x secant x tangent x minus secant x, and that's 5. Now here we go, the chain rule. So what we want to do is make sure we remember how this works. So remember, we're assuming that you, not you, that's for the other one. We have y is actually a function of another function. And so what we're doing is saying, well, it's in the assumption that u is a function of y, that y is a function of x. Okay, so let's choose something to represent u. Okay. And so let's say that u is 7x okay. So y, if that's the case, oh, I just realized du dx. And dy du, well, dy du comes from here. Actually, I just realized, I think I wrote this part backwards. I'm just going to confirm this. I don't want to get anybody confused here. No, I had it right. Okay, just making sure. That's the beauty of this. Oh, no, I did have it backwards. Sorry. This one was, I knew something wasn't right. Why? Here we go. I knew something was backwards. Y is f of u, and u is g of x. That's better. Okay, so for this type of chain rule problem, y is a function of u, and then u is a function of x. Okay, that's better. Anyway, once we got that straight, so we're going to let u stand for 7x minus 4, 7x minus 4. And by doing it that way, this function can be written as y equals 6u to the third power. So when you choose a u, what you're trying to do is create a polynomial which is as simple as possible. So that being the case, if I let u be 7x minus 4, du dx, based on the power rule, is 7. What about dy du? Well, we just determined that y equals 6u cubed based on the power rule. And again, it doesn't matter what letters we use, the power rule never changes. That implies that dy du is 18u squared. Okay, so we can think of this as having k equals 6, n equals 3, then nk to the n minus 1 is 3 times 6 times x to the 3 minus 1. So if you're using x, okay, over here we're using u, but it's the same idea. Okay, so there's our dy du. Now, you can see all we still have to do is plug everything in. Make one substitution. So in other words, we have 18u squared. And we've already determined that du dx is just 7. So that's going to be now we want dy dx, but we know that u is equal to, or we chose u to be equal to 7x minus 4. So when we're done, the final result will be right there. Okay, so that's the chain. All right, so the chain rule is kind of involved, but we run into it quite often. Oh, now this is obviously it's a trig function, but it's a function of a polynomial of x. So we can use the chain rule here too by using the same setup. For example, actually, let me do one thing here. If you've never seen this before, if you're using a Word document and you get tired of switching around, scrolling up and down and up and down, you can create a split here. So you can scroll around independently. It's very helpful. All right. So here, let's try u equals 9x plus 2. So y is 10, and okay, now let's try this. Du dx will be a breeze because we don't need this anymore. If u is just 9x plus 2, based on the power rule, du dx would just be 9. On the other hand, dy du, we have to go back and consult with our chart. Unless you've memorized them, the derivative of the tangent of x is secant squared of x. Okay, so when we consolidate these, we're going to have secant squared u times 9. So we're going to end up with remember, we defined u to be 9x plus 2. So therefore, our final result is 9 secant squared of 9x plus 2. Beautiful. Now, we're saving this for last. Implicit differentiation, because this one actually does require the chain rule, although we applied it in a somewhat different way, as you recall. So what's going to happen here? So let's remind ourselves how this is set up. So we're going to say, this is what I was doing before incorrectly. I was thinking of implicit differentiation and I was doing it incorrectly. So u for this is f of y is g of x. And what we know here is that for each term, what we can do, first of all, let's do this. Oh, one more thing. Don't forget about this part. Du dx equals du dy. So we can treat each term individually. Now, if I differentiate both sides, oh, you know what I just realized? Oh, there's a typo here. This wasn't supposed to say this. Oh boy. So yeah. If you looked at this before, you might have been confused. I just realized unfortunately I made a typo there. That y wasn't supposed to be there. So now it's more clear why we must use implicit differentiation. So, oh, that's so frustrating. Anyway, so here's what we're going to do. So we're going to take the derivative of both sides. And two of these three terms are very straightforward. This one will just become 12x from the power rule. So then it goes to 0. And that leaves this one. What do we do with this? Okay. So what we're going to do is let u 3y squared so du dx equals du dy y dx equals, so we plug some numbers in. Now, we don't have an expression for dy dx. That's what we're solving for. So it just ends up being 6y dy dx. So when we gather all this information together, we have 12x plus 6y dy dx equals 0. So I'm going to subtract the 12x from both sides. I'll just divide out the 6y. That just leaves me with negative 2x over y. All right. Now, one more. That's it. and this one is typed correctly, I see. We're going to have the derivative of x squared y equals the derivative of y. And so this just becomes dy dx. This is just 0. This is the one that's going to be a lot of fun. So here's what we have to do. We're going to apply the product rule here. Okay. All right, hold on. So that's going to be, so just like the product rule when we're not doing implicit differentiation, it's the first term times the derivative of the second plus the second times the derivative of the first. Okay, so now we bring all this stuff together. Now remember too, we had a 0 that drops out. And now we actually have two dy and dx's here that we can consolidate. And then while we're at it, let's subtract this 2xy. I'm going to rewrite this as 2xy and subtract it from both sides. And then we're going to factor out this dy dx. And then the last step is simply to divide. Oh boy. Yeah, with this tablet, I have to be careful where I write. There we go. All right. So if you're able to do all of those, then you're in good shape, I think, for the problem sets that you'll be doing. If not, especially the chain rule and the implicit differentiation, um, there's more examples in the book that you can look at. And if you're really pushed to the wall, I mean, you certainly can always ask for a Zoom session if you're really stuck with some of this stuff. But if not, you shouldn't have any problems with this, at least this chapter. Chapter 3 is going to be a little bit more involved. Explore a little more in detail what's actually happening with differentiation. But okay, so hopefully this helped. And so the next session we have, we'll dive into chapter 3. Okay, all right, so I'll see you then.